Okay, first one up here, two examples of a heterogeneous mixture. So what do you have for heterogeneous?
Pizza.
Sure, pizza. Definitely looks the same or different throughout the pizza. Something else?
Chocolate chip cookie.
Chocolate chip cookie sounds good. And homogeneous? Looks this. Sugar water? Something else?
Beer.
I don't think I would go with beer.
No.
Bubbles.
Bubbles.
A little bit of foam on top. Yeah. How about a Lego? Are you okay with that? A Lego? Say again?
What is that?
A Lego? What is a Lego?
Building brick.
You missed out on a good Christmas. What else could we put on here?
Would blood be heterogeneous? Because if you look under the microscope, you're going to see all the different things, or would it, since you're just looking at it, would it be?
I'm pretty sure the book says it's heterogeneous,
Okay.
but I'm going to disagree with the book because it also says in there to the eye. And so, I mean, it's silly. If you're going to use magnification as your example, if it's heterogeneous or homogeneous, then I could just keep zooming in, and eventually my homogeneous thing isn't going to look homogeneous at all. So it's to the eye. So I would say blood would be a homogeneous solution. But butterscotch pudding, are we okay with that? Being homogeneous? Mayo? Okay. So differences between physical and chemical changes. I saw a little bit of discussion about this on the discussion board, and somebody, I don't know who it was, said something about you get changes of state. Yeah, but the change of state has to be, the substance has to be the same. So if I have a solid and it goes to a liquid, the thing has to stay the same. And what I mean by that is if it's water, it's got to stay water as a liquid. And when you eat something and it goes from a solid into a liquid or a solid into a gas, it's a totally new something or other. It has a completely different chemical formula. So that's definitely a chemical change, not a physical change. So what's the main difference between the physical and chemical changes? The formula of the substance has to change in a chemical reaction. And in physical, really we just get a change of state. No formula change. So you have H2O as a solid turning into H2O as a liquid. So that's just a chemical change because on each side of the arrow I still have a water molecule. But if I've got H2O as a liquid and it turns into H2 and O2 gases, all right, well, is that a physical change because I just changed from liquids to gases? The things on both sides of the arrow are definitely different from each other, so then that's going to be an indication of a chemical change. What are the three things that you would see that would hopefully let you know that, yeah, you just witnessed a chemical change?
Change of color?
Essence of gas.
And? Precipitate. Okay, so I've got color change. I've got gas created, and I've got precipitate. Does that mean when I'm boiling water, that's an indication of a chemical change because I'm seeing bubbles? Because we know we've just added heat to it. So if you can take two substances and mix them together, like vinegar and baking soda, and all of a sudden bubbles are formed, I didn't add any heat to that. I didn't to change its state. I'm actually getting a totally different chemical substance because at room temperature, baking soda and vinegar are solids and liquids, and then when they mix together, all of a sudden I get a gas without any added heat. So that must be a new thing that was made. All right, so choose a problem, explain how you use the scientific method to solve said problem. So does anybody come up with something good for us?
Your TV breaks.
Your TV breaks? Okay. So you have a problem, your television breaks. So what do you do next? So there's no picture coming through on the TV, so you probably aren't going to do a whole bunch of research, but you'll probably think about in your head what other things that have made my picture not come through my TV. And so, yeah, you're going to investigate cords. You're going to maybe call a friend and say, is your TV working? Call a cable company, is there cable? Something of that nature. Is it storming outside and I have dish? And so that's the reason. So you'll think about a whole bunch of different reasons as to why this could be, and then let's say you do have dish and it's storming outside. Your hypothesis might be that my dish was blown, or there's water in the dish or something like that, or there's just too much interference from the atmosphere, and then you go outside and look. Has it been moved? Has the wind shifted it? Something of that nature. And then you would try to fix the problem and then go back inside and check to see if the TV is working or not. So, yeah, certainly. Unit, how about a definition for the unit?
Lego.
Say again?
I said a Lego, something small that makes bigger things.
How about a piece? A piece of something? A little more to that though. What else do we have to know about it?
With standard measurement?
It's got to be a standardized thing, right? Everybody has to agree that this piece is a piece of, and that piece is of a certain size, and we all agree that it's of a certain size. And usually we use it to measure things. And so when we measure things, normally we're thinking about feet or pounds or something like that, but it could be something more simplistic like dollars. That's still a unit, or quarters or nickels or something like that. Why was the metric system developed?
Create a standard?
What?
To create a standard?
Yeah, everybody, whole world. We're hoping that everybody's using the same units so we can all, does anybody know what a famous unit snafu was between the English system and the metric system? Cost several $100 million. About 15 years ago, we sent a probe to Mars. One calculation was done with units using the English system, and the other was done using the metric system, and the two scientists didn't realize that their units weren't the same, and so the probe crashed. It hit Mars at like 400 miles an hour instead of 40 miles an hour because their units weren't the same. That did not go over very well. And what value is it based on?
Hours of 10.
Just 10. Tens, powers of 10. Okay, so we're going to convert this into a decimal format. So I've got 5. I'm going to move the decimal place 5 spots. So 235,800. Do I put a decimal after that? No, I do not. How many significant figures are in the given number?
4.
There's only 4. If I put a decimal after that 0, what would that tell me? That I'd have 6. And so you can't change the number of sig figs unless you redo the measurement, and we didn't measure anything. Okay, so we're going to put this guy into scientific notation. So 6.5895 times 10 to the 4th. Okay. And then we're going to want to put this next one in a decimal formation. So I've got 0.005894. How many significant figures are in that third?
Six.
4. Those zeros are placeholders, right? The easiest thing to do is put it into scientific notation and then count. So how many were in the given? 4 for sure, right? So just because I put those zeros in there, that doesn't mean that I've added significant figures to it. I've still got just the 4 sig figs. And then this last one, I got a 2.93 times 10 to the negative 4th. So how many are in this last one, sig figs? 3. You might want to say 6 with the given value, but those zeros, again, they're just telling you where the 9, 2, and 3 belong in a decimal. All right, so we want to convert 285 inches into meters. So I've got 285 inches, okay? And I want to cancel that inch thing out so I can get closer to meters. So where do I need to put the inch unit? On the bottom. So if I have the inches in the denominator, then I can cancel the inches out in the numerator. So I'm going to go into meters, and so we have a nice conversion of 1 inch is 2.54 centimeters, and so then my inches will cancel out. And I don't want centimeters, I want meters, so where's my centimeter unit going to go? Also on the bottom. So centimeters down here, and there are 100 centimeters in 1 meter. And so then I can do my math with this, and somebody have a value for that? 7.239 meters. And then how should my answer look? 7.24. So since I've only have 3 significant figures in my given, and how come I don't just have 1 significant figure because it says 1 inch or 1 meter? So if I'm looking at this problem and I'm trying to figure out how many significant figures I have 3 significant figures for this. And don't I have 3 here and 1 there and 1 there and 1 there? Remember what significant figures is doing for you. What does it manage? What was our reasoning behind even using them at all? It measures accuracy in your answer. So this 285, this is measured to 3 numbers of accuracy. How accurate is this? Is it just 1 accuracy? Is that as accurate as it gets?
That's exact.
It's exact. It's a definition, right? It's infinitely accurate. So you can have as many zeros after that 1 as you want. So the reason I'm not going to count the 1 meter as 1 significant figure is because that is a definition. There is no inaccuracy in it. So this is all about inaccuracy or accuracy. And since the 285 was the only measured value, the rest of those things are exact. So I don't have to worry about those sig figs. So then my answer here would definitely be 7.24 meters, because the 3 rounds up to a 4 when I get rid of the 9. All right, so now we're gonna go feet per second into miles per hour. So I've got 24.5 feet per second, and I wanna get rid of both the feet and the seconds. We can do the feet one first, so I'll put feet in the denominator, and I have 5,280 feet is equal to 1 mile, and so the feet cancel out. And then if I put 60 seconds up here, I can cancel out those seconds with 1 minute, and I can do that again for 60 minutes, gives me 1 hour. Cancel out the minutes, And anybody have a number for that one? 24.5 divided by 5,280 times 60 times 60. I get 16.7 miles per hour. And are we okay with that for the significant figures? 3? Because the other things are definitions, so don't worry about the sig figs with those. All right, what is the mass of a piece of wood with a density of 0.9 and a volume of? Okay, so I've got the density equation is density equals mass divided by volume, but I'm not even going to bother using that. What am I looking for?
Mass.
I'm looking for the mass, right? So I'm just going to build myself a little railroad track where my answer gives me a mass unit, and in this problem it's grams. So I've got 2 pieces of information, and do either of those pieces of information have a gram unit in it?
Yeah, the density.
Okay, so I'm going to write 0.92 grams per milliliter right there. How come?
So
What do I want my answer's unit to be? Grams. So do I have the gram in the correct position? It came with a milliliter, but the gram is in the numerator right where I want it. Okay, so that's totally fine. But now I just need to get rid of the milliliter portion of it. So I have another number with centimeters cubed, and we know that the centimeters cubed are equal to milliliters. So then I can just throw up 355 milliliters here and cancel that out. So now what unit's left?
grams.
Grams. If you did the equation, it would have you multiply the density times the volume, but I don't need to bother with the equation. I'm just looking for a unit. And if the railroad track thing gives me the unit I want, then that's my answer. So 355 times 0.92. And I got 362.6 for my answer. And then what answer should I actually report?
360.
I report 360. How come just 360?
We have 2 significant figures in the density.
There's 3 sig figs here, but there's only 2 sig figs here, so my answer can only have 2. So if I write 360 and no decimal place after the 0, that's telling me that the 3 and the 6 are significant, but the 0 is not significant.
The answer is 326.6.
What? Did I dyslexia that? Oh yeah, totally.
Yeah.
326. $326.6. And so then I'm going to have this equal
330.
330 grams. That's better. This triangle of dots, that means therefore. So if I do that, that's like, we got an answer, and then therefore we know what the sig figs are, or therefore we know something, and then the answer changes to something else. Are we okay with that? Yeah.
I just don't know how to round it out to 330 instead of 327.
How many sig figs do we have in the given information? 3 for the 355, right? And how many for the density? Just 2. So I can only write 2 for my answer. And so if I wrote 327, that would be 3. So if I write 330, then the 3 and the 3 are both significant, and the 0 without a decimal means the 0 isn't significant. Right. How could I write this another way to make it more clear that there's only 2 significant figures? Right. You could write 3.3 times 10 to the second grams. And then that's showing there's only 2, but it's kind of a lot of writing to write 330. So just drop the decimal and that shows 2.